This video is for Math 95, and in this video we're going to talk about complex numbers. So as an introduction, let's talk a little bit about our number system. Okay? The most basic form of mathematics is counting, and so the most basic set of numbers are what are called the natural numbers or the counting numbers. Some people include 0, some people don't, and some people just like to argue about whether or not 0 is included in there. I'm going to include 0. If you don't want to, you don't have to. So the natural numbers are the counting numbers. They're the positive whole numbers that we're familiar with. These are the most basic form of numbers. And for me, this is kind of interesting culturally, because if you look all over the world at how different cultures approach mathematics, you can kind of see that people create mathematics for what they need it to do. Okay? And most cultures need numbers in some way to keep track of things, to keep track of years, to count how many people there are, and so on. Let's see here. So, the thing about the natural numbers is that you can write an equation, right? Let's say you take an equation like x plus 5 equals 1, but the solution, so now we're only using the natural numbers in this equation, okay? But the answer to this equation is not a natural number, right? If we subtract 5 on both sides, we get x equals -4. Now, Indian mathematicians were some of the first mathematicians that I'm aware of to run into negative numbers and to work with negative numbers. And they did this in calculating debts, right? If people were borrowing money, then they were indebted to somebody else, and those debts were considered to be a negative value for the person who owed the money. Okay. So we can continue doing this. Oh, so now the fact that we need these negative numbers, right, allows us to extend our number system to include both the positive and the negative whole numbers. Okay? All right. Now, what if we wrote another equation, like, say, 3 times x equals 2. So again, we're just using natural numbers, but the answer to this equation is not a natural number. It's what's called a rational number. That number set is represented with a Q for a quotient, right? Because the ratio and a quotient are synonyms for the same thing. Let's see here. And these are the fractions where a and b are both in the integers. So let's talk about this a little bit. These double-barred capital letters are how mathematicians represent these sets of numbers if they want to talk about them. So the N stands for natural numbers. The Z comes from German. The German word for numbers is Zahlen. And then I said a minute ago, the Q stands for quotient. Now, I mentioned that the Indian mathematicians worked with, I think, all of these sets of numbers. The Greeks tended not to work with the negatives. They had just the whole numbers and the fractions, and they did extensive work with those numbers. Now, something that the Greeks ran into, and this caused them considerable difficulties, right? If you take a square that's 1 on all sides and you draw this diagonal here, now you've got a right triangle, and we know from the Pythagorean theorem that says a squared plus b squared equals c squared, so 1 squared plus 1 squared has to be c squared. So c is the square root of 2. Now, the Greeks thought that all numbers were a ratio of whole numbers, a rational number. Okay? This square root of 2 is not a rational number. It's what's called an irrational number. And it's approximately, we can approximate it 1.414 dot, dot. It's a non-terminating, non-repeating decimal. You can see that this is pretty close to 1.4, which is 14 over 10, which is 7/5. But you can see that if you square 7/5, right, 7/5 squared, you get 49 over 25, which is not 2, right? That's the whole idea. The square root of 2, when you square it, you should get an answer of 2. So this is not a rational number, so it's not included in any of these number sets, and we have to extend our conception of numbers again, and this leads us to what are called the real numbers, okay? And every real number, like the square root of 2, has a place on the number line, okay? And every place on the number line corresponds to a real number. And the number line, I think, is a really good way to represent real numbers, and even at the highest levels of mathematics, that's how the real numbers are defined, as on the number line. Okay, so let's talk about the real numbers for a minute, right? So if you have a positive number like 4, and you square it, you get another positive number, which is 16. And if you have a negative number like, say, -3, and you square it, you get a positive number. Positive 9 in this case. So what if we had an equation that said x squared equals -1? Well, if you take a positive number and square it, you get a positive number. And if you take a negative number and square it, you also get a positive number. So what kind of number can you square and get a negative answer? So this leads us to our last extension of the number system for our purposes, is that if we square root both sides here, this will give us x. And over here, we'll get the square root of -1. And this is a number that gave mathematicians a lot of difficulty. One of the first European mathematicians to work with the square roots of negatives was an Italian mathematician named Girolamo Cardano. And he was in the middle of making all these calculations and came across a square root of a negative and said, well, I'm not going to worry about this right now. We're just going to carry it around with us and see if it can help us out anywhere. And what he found out was that if he did that, he arrived at an answer that was helpful to him. Okay? And so this leads to the last extension of our number system, what are called complex numbers. And the fundamental idea about complex numbers is that they are two-dimensional. All right? I'll talk more about that in a minute. And they're represented in what's called a plus bi form, where a and b are real numbers, but I is defined as the square root of -1. And so that's kind of the same thing that Girolamo Cardano was doing, just sort of carrying this number around, calculating with it as best he could, and not really knowing where it was going to lead. So human beings today still have kind of a resistance to these complex numbers. In fact, a lot of textbooks refer to them as imaginary numbers. And for a couple hundred years after Cardano, people occasionally worked with them, but didn't really know that they were good for anything. But here's the thing. These complex numbers are two-dimensional. Okay? You've got a real number part, which is the a part, and then you've got a complex part, which is the bi part. Okay? And so the real number line is just like it always is, but on the vertical axis, you get these multiples of I. And so if you wanted to graph a complex number, like say we have something like 3 minus 2i, you'd go over 3 on the real number axis, and then go down to minus 2i, and there's that number 3 minus 2i. Now, why does this make any difference? In the 1800s, when scientists were beginning to really work with electricity, right? In the 19th century, this was a period of time where people were just beginning to understand how to work with electricity. They were developing the telegraph in the 1830s, and then the telephone in the 1880s and 1890s, along with electric lights. And a lot of the laws that govern electricity really fit into this two-dimensional number system, and they become very, very useful. If anybody ends up going on to be an electrical engineer, you will find yourself working with complex numbers. Okay, so let's see here. There's an explanation of where the complex numbers come from, why people use them. And so let's take a look at some of these problems. So the assignment starts out with just some square roots. So here's the thing. I talked a minute ago about how mathematicians define the square root of -1 to be this quantity I that we don't really know a whole lot about, but we're going to work. In fact, we're going to work with it. In fact, that's what Girolamo Cardano said. He said, this is a fantastical number, nevertheless, we will calculate with it as best we can. Okay, so if we want to calculate the square root of a negative number, what we can do is break off this piece that has a -1. So if we want the square root of -9, we can split this up as the square root of 9 times the square root of -1. Well, the square root of 9 we know, that's 3. The square root of -1, we're just going to call it I. So the square root of -9 is going to be 3I. Okay? And so we can continue to do that. So in problem 2 here, if we've got the square root of -36, we can split that up. Square root of 36 is 6. Square root -1 is I. And there's our answer. And you can skip this middle part if you want, right? The whole idea here is just square root this number as if it were positive, and then because it's negative, we need to have the I attached to it. So like in problem 4, where we've got the square root of -144, square root of 144 is 12. Because it's negative, we include the I. Problem 6. Square root of -121. Square root of 121 is 11. And then square root of -121 will be 11I. And problem 8. Square root of -81 is going to be 9I. Okay, now in problem 10, we get to numbers that are not perfect squares. Square root -3. Okay, so this depends on your calculator. So we can always work around the calculator, right? If your calculator doesn't like to take square roots of negatives, that's okay. We can square root a +3 and then just tack the I onto the end of it. So if we square root the +3, that's about 1.732, and then the square root of -1 will be I, and so there's our approximate answer, good to 3 decimal places. So you can try to square root these as negatives. So let me show you what happens on this calculator. This calculator is kind of weird, and I'll show you why in just 1 minute here. Okay. So let's get a good look at the calculator. So there it is. If we square root -3, it's going to give us an error message, okay? But we can get around that if we go into mode, come down here. Instead of just looking at the real numbers, we also want the A plus BI numbers. And then if we go back and square root this -3, there it is, 1.732, and then you can see that little I on the end there, okay? So your calculator might have difficulty trying to square root negative numbers. If it does, see if you can get around it. If you can't, just square root the positive number and put an I on the end of it. Okay, let's see here. Problem 12, we're looking for the square root of negative 12. So that's not a perfect square, so let's get a good approximation for that. 3.464 is the square root of 12, and then 3.464i is the square root of negative 12. Problem 14, square root negative 240. So if we square root 240, that's going to be 15.492. And then square root negative 240 will be 15.492i. And we'll do one more of these. Problem 16, square root of negative 60. So we get a good approximation for the square root of 60, 7.746. And then because it's negative 60, we tack the I on there. Okay, so that's the first part of the assignment. The second part of the assignment is how to calculate with complex numbers. We want to add, subtract, and multiply. Dividing with the complex numbers is kind of tricky, and so we're just going to forget about that for right now. If you're interested in that, I'd be happy to talk with you about it. Okay, problem 18. We want to add 7 plus 15i plus 11 minus 14i. Okay, so the key here is that we're adding, so we can just add these numbers together. 7 and 11 make 18. 15 minus 14 is positive 1i. You can put the 1 in there or not put the 1 in there, depending on how you want to do it. Okay, I'm just going to call it 18 plus I. Problem 20 is addition as well. 6 plus 4i plus negative 2 minus 7i. So 6 and negative 2 make 4. Positive 4i minus 7i makes minus 3i. Okay, problem 22 is subtraction. So this is where you have to be a little bit careful. And if you see similarities between this and doing regular algebra, you're not wrong. There are a lot of similarities between working with complex numbers and combining like terms. Okay? There's some important differences, and I'll talk about those in a few minutes. Here, this subtraction has to be distributed. It's going to affect both of these numbers. We're going to have 9 plus 5i, and then positive 2 and minus 4i. Now we can just combine our like terms. 9 and 2 make 11. 5i minus 4i is positive 1i. Okay, let's see here. Problem 24. We've got negative 8 plus 5i minus negative 6 minus I. So again, the subtraction here in front of the parentheses has to be distributed. That first parentheses is going to stay the way that it is. Here we'll get a positive 6 and a positive 1i. So let's see here. Negative 8 and positive 6 makes negative 2. 5i and 1i makes 6i. And there we go. Negative 2 plus 6i. Okay. All right. Problem 26 is a little bit more involved. Here we've got 3 complex numbers. Negative 4 plus 11i. And then we're going to add negative 2 minus 4i. And then subtract negative 7 plus 2i. Okay. So these two parentheses aren't going to change. We're going to have negative 4 plus 11i and then minus 2 minus 4i. This subtraction has to get distributed. That'll give us positive 7 and minus 2i. And now we want to combine our like terms. So we've got our real numbers here. Negative 4, negative 2, and positive 7. That should make positive 1. And then we've got our complex parts. Negative 2i, negative 4i, positive 11i. And let's see, this will be 7i minus 2i, so positive 5i. But let's look at a couple more of these. Let's see. Problem 28. What do we get here? We've got a 12 minus 2i minus 4 minus I. And then from that we want to subtract 2 plus 5i. Okay, so this subtraction or negative needs to be distributed, so that'll give us 12 minus 2i minus 4 plus I. So that'll be 8 minus I. And then this also has to be distributed, and that'll give us minus 2 minus 5i. And so in the end, we'll come out with 6 for the real numbers, and then negative 6i for the complex piece. Okay, let's look at number 30. Number 30 is a little bit tricky. Here we've got 15 minus 7i, and then minus in front of the brackets, 2 minus 7i plus 1 plus 5i. So what that means here, now if you look at this problem 28, I didn't really worry about the brackets because there was nothing in front of them, right? And so we can put the brackets here, we can put the brackets here. In the end, we're going to come out with exactly what I had written there before. Now in this one, this subtraction is going to hit everything in these parentheses, or in the brackets. So let's work in the brackets first. 2 minus 7i plus 1 plus 5i, right? So this plus is not going to change anything. And then out of that, what are we going to get? 2 plus 1 is 3. Negative 7i plus 5i is negative 2i. So now that we've got that, this negative sign now has to get distributed. So that'll give us 15 minus 7i minus 3 plus 2i. So that'll be 12 minus 5i. Okay, so there's the adding and subtracting. And then, starting with problem 31, we get into multiplying. So this is where it's a little bit different from just doing straight algebra. So let's talk about this a little bit. Right? So I've said that we define the square root of negative 1 to be I. And I keep talking about the definition of a square root, right? The square root of 25 is 5 because 5 squared, which is 5 times 5, is equal to what was inside the square root there, 25. So, if we say that the square root of negative 1 is I, that means when we do I squared, or I times I, we should get what's inside the square root, which is negative 1. So I squared is equal to negative 1. That's a really important idea. Okay? And that comes from the definition of a square root, right? If the square root of negative 1 is I, when you square the I, you should get negative 1. So, understanding that, let's look at a couple more. Let's look at some of these multiplication problems. Problem 32, we've got 7 minus 2i times 3 plus I. So, the multiplication here works just like the multiplication in algebra, what people sometimes call FOIL, right? We have to distribute the 7 there and there, 21 plus 7i, and then we have to distribute the minus 2i there and there. That'll be negative 6i minus 2i squared. And just like we do in algebra, we're going to combine our like terms, plus 7i minus 6i is plus 1i minus 2i squared. Here's where it gets different. We just said I squared is negative 1. So what we're looking at here is actually 21 plus I minus 2 times negative 1. That's going to be 21 plus I plus 2, or 23 plus I. There's our answer. If you multiply these two complex numbers together, you get this complex number here, 23 plus I. All right, let's look at a couple more. Problem 34, 9 plus I times negative 5 plus 7i. Okay, so we're going to do the same thing we did in problem 32. We're going to distribute the 9 here and here, get negative 45 plus 63i, and then distribute the 1i there and there. That'll give us minus 5i plus 7i squared. So, combine our like terms in the middle, minus 45 plus 58i plus 7i squared. And then replace that I squared with a negative 1. So negative 45 plus 58i minus 7. Now you've got a negative 45 and a negative 7. That makes negative 52 plus 58i. And that's our answer for multiplying those two complex numbers together. All right. Let's look at a couple more of these, and then that'll be it for this topic. Let's see here. Problem 36. 1 minus 6i times negative 4 plus I. Now, one thing I want to say before I go and calculate this is I just want to talk about a mistake that I frequently see people make on the final exam. And here it is. Notice the difference between these problems, which involve multiplication, and something like problem 18, which was about addition. Okay? This plus sign indicates the addition. That's why we got 18 plus 1i. Here, if these two parentheses are just bumped right up against each other, that means we're doing multiplication. And so it's really important that you understand the difference between addition or subtraction versus the multiplication of these two numbers. Okay? So I'll just throw that out there. Like I said, it's a common mistake that I see people making, and I'm just encouraging you not to make that mistake. All right, so this is multiplication, and so again, we're going to distribute here and here. And that'll give us negative 4 plus I, and then distribute the negative 6i. Let's see, that'll be positive 24i minus 6i squared. So we get negative 4 plus 25i minus 6i squared. And now let's plug in a negative 1 for that I squared. Negative 4, 25i plus 6. So that'll give us 2 plus 25i. So there we go. All right. Problem 38. We've got 3 plus 2i squared, and that means 3 plus 2i times 3 plus 2i. Don't try to just square both of those, because that's not what it means. To square something means to multiply it excuse me, by itself. And so that's what we have to do in this problem. Okay, so we're going to distribute the 3. That'll give us 9 plus 6i. Distribute the 2i, and that'll give us another 6i. plus 4i squared. So 9 plus 12i plus 4i squared. Plug in the negative 1 for the I squared. And that'll give us 5 plus 12i. All right, let's look at another one of those. What do we have here? Problem 40. Negative 3 plus 8i all squared. So, again, if you square something, that means that you should multiply it by itself. So there we go. And now we have to distribute the negative 3. That'll be positive 9 minus 24i. Distribute the 8i. We'll get another minus 24i. And then a positive 64i squared. So 9 minus 48i plus 64i squared. Replace that I squared with negative 1. So 9 and minus 64, what is that going to give us? Negative 57 minus 48i. And there we go. Okay. Problems 41 and 42 are a combination of these computations. Okay? Computation has the same root as computer. It means to do arithmetic. Okay? So in problem 42, we've got a combination of different computations. We've got some multiplying going on, and then in the middle, we've got some addition. So let's see how this is going to work out. We've got 10 plus 3i times 1 minus I, and then we're going to add whatever we get from that to 8 minus 5i times negative 4 plus I. Okay, well, let's see. Let's give me some more space here. Let's see how much I need. All right, so first we have to multiply here. So this will be 10 minus 10i plus 3i minus 3i squared. So I'll keep that in parentheses. Over here we're going to get negative 32 plus 8i plus 20i minus 5i squared. Okay, now let's combine this a little bit. 10 minus 7i, and then I'll replace that I squared with a negative 1. So this is going to be 10 minus 7i plus 3, or 13 minus 7i. In here, let's see, what do we get? Negative 32 plus 28i, and then replace that I squared with a negative 1. So this will be negative 32 plus 28i plus 5. So the negative 32 and the plus 5 make negative 27 plus 28i. So you know that if you add a negative number, it's the same as subtraction. So here we've got 13 and negative 27. That should give us a negative 14. And then negative 7 plus 28i is going to give us a positive 21i. And there we go. So again, we kind of end on the most complicated problem. But the ideas that we're using in this problem are the ideas that we practiced in the earlier parts of the assignment. Okay? So hopefully you'll be able to work through these problems without too much trouble. And as always, if you have any questions as you're working through them, please let me know. Thank you.